we started with something like e to the minus h t. Right? And we evaluated that to between some state, it could be any state that we could start with, and on the left-hand side, some initial state consisting of the values of fields on the surface t equals 0. So that corresponded to fields on the surface t equals 0 and e to the ht. And if you take the limit, the time goes to infinity, the only thing that will survive in here will be the projection operator onto the slice. Now, e to the minus ht is analogous to e to the minus iht, which is the time development operator. The way that you calculate it, the way you calculate any exponential is by dividing it up into lots of little infinitesimal times, let us call them, which is not really a time, but dividing it up into lots of little pieces and multiplying them all out together. E to the minus h epsilon multiplied together enough times, namely t over epsilon times, gives you e to the minus ht. So you divide time up into lots of little segments, and multiplying operators means calculating transition matrix elements of e to the minus h epsilon between neighboring times, and then summing over the intermediate states, and the intermediate states are just the data on these horizontal lines. That leads, I mean, I'm not going to go through the whole derivation of path integrals. That leads to the expression that this is just e to the, this is the integral over the fields on the intermediate sections in here of e to the minus the action integral L dt, where this L is not the real Lagrangian of the system, but it's the Lagrangian in which t goes to it, so that we're talking about the Euclidean path integral. I don't think I want to spend a lot more time on that, because most people in the audience, that's more or less standard, and if it's not, the place to look is to look up the Feynman-Helmont theorem. Now, then, after having established this relationship, what I argued is you could evaluate exactly the same thing another way. There's a kind of transfer matrix calculation where you multiply a bunch of transfer matrices together. Transfer matrices just meaning operators which represent infinitesimal time evolution, multiplying them together, but then you can slice up exactly the same path integral into little infinitesimal sections like this, and think of transfer matrices which take you from one section to the next in this direction, and that gives you exactly the same ground state, except now expressed as a transition amplitude between fields on the left and fields on the right, where now the thing which replaces the Hamiltonian in this formula here is the Rindler Hamiltonian, which is this angular Hamiltonian here. Now, those steps are worked out in my book. They are the Feynman-Helmont theorem, except with this little bit of trick of replacing evolution in vertical time by evolution in angular time. Okay, if there are no other questions on it, yeah.
Sorry, hopefully this will be. The last time you had a box B and a system A, and you were talking about the entanglement entropy between.
Right.
And so initially you had the entanglement entropy being 0. Right?
Yes.
And then the thermal entropy would transfer, and then at the end the entanglement entropy was 0.
Right.
Is that reasonable to suppose that the entanglement entropy would be 0?
Now we're talking about conventional quantum mechanical systems. We're not talking about black holes yet.
Okay.
Is it? All right, we're talking about conventional quantum systems. In the beginning, there was nothing outside the box. only things inside the box. There's no way there can be any entanglement entropy between the inside and the outside, since there is nothing outside.
But okay, so you're saying that if the system is, I mean, there's vacuum, but you're saying that entanglement will always be zero for vacuum.
Yeah. I'm not worried about the details of entanglement. Think about this as non-relativistic physics, for simplicity. Non-relativistic physics. Things on the outside mean things on the outside. I'm not worried about the delicate entanglement entropy at the boundary of the box. That's a secondary issue. Let's think non-relativistic quantum mechanics, where there's particles can be inside the box, they can be outside the box. The thing which creates entanglement is the possibility that that a particle is in a superposition of being inside the box and outside the box. But if the initial particles are all inside the box and there's nothing outside the box, then there's no entanglement entropy. If all the particles are outside the box and there's nothing left inside the box, there's also no entanglement entropy. So the entanglement entropy has to go from 0 to 0. In between, it gets large. All right. I am not going to tell you a great deal about the technology and technique of using string theory. In fact, I'm going to talk about string theory a little bit today, a little bit more next time. The enormous technology that has been created by string theorists for evaluating black hole entropy, it's quite marvelous. But my own way of thinking about physics is in terms of principles, to try to find consistent sets of principles, and consistent sets of principles often involve Gedanken experiments, trying to think about how this can be consistent with that. And for me, string theory is largely, at least in this context, in this context, it's largely a mathematical structure which seems to be robust, which seems to be consistent, and which seems, if not to describe our world, to describe some world. Because it describes some world, and because that world has black holes in it, because it has gravity in it, one can address questions such as, in that world, which is, as I said, not necessarily our world, in that world, do black holes lose information? Do black holes cause information loss? If the answer is no, then that doesn't mean that string theory is the right theory. What it does mean is there's some hole and something missing in Hawking's arguments. That's what it means. It means Hawking was wrong. It doesn't mean that string theory is right. So for me, string theory at the moment, for our purposes, is a context in which we can test out principles. The principles came not from string theory, but really came from people like Hawking, like Bekenstein, like Don Page, like 't Hooft, like myself, thinking about Gedanken experiments. So what I'm really going to talk about today is a set of 3 clashing principles, and how they affect the basic principles of information, locality, and that kind of thing. I think the bottom line is that quantum field theory has seriously misled us when we tried to push it into the domain of quantum mechanics. It has seriously misled us about the way that information is localized in space and in time. In fact, it has misled us by telling us that information is localized in space and time in a way which I think, thinking hard about the basic principles, tells us cannot be the case. I want to talk about those 3 clashing principles, or perhaps 3 clashing laws of nature, why they clash, how they clash, and what the resolution is likely to be. The first clashing principle, the first principle, well, one principle can't clash. It's just like the sound of one hand clashing. One principle is what I'll call the laws of quantum information, and by that, quantum information. By that, I'm not going to mean the sort of things that the information people think about. I'm just going to use that to summarize the following picture, or to summarize the idea of quantum information by the picture that I drew last time, entropy versus time, and to indicate the various kinds of entropy on this diagram and how they relate to each other. The system that we studied could have been a box, outside world. B could have stood for black hole, and A could have stood for the place where photons go when they evaporate, again into the outer world. Or B could have stood for a bomb exploding inside a box with a tiny hole, which lets photons out. They're all pretty much the same, or at least the laws of quantum information would say they are the same. All right, so how do the entropies evolve? First of all, there's the thermal entropy inside the box, or the thermal entropy of the black hole, which has been suddenly assembled. Let's think of the black hole as being suddenly assembled, and the entropy goes up. In the case of the black hole, it goes up. I want to draw these with dotted lines. The entropy goes up. The thermal entropy of the black hole goes up. And then in time, the box gives up its particles. The particles leak out, and the thermal entropy goes back down to zero inside the box. So that's the thermal entropy inside the box. Okay. Then there's the thermal entropy on the outside. The thermal entropy on the outside starts at zero. I'm ignoring any possible entanglement entropy between the inside of the box and the outside of the box. That's negligible. And by that I mean entanglement entropy in the ground state, you know, what they call, what do they call it? This is a funny name for a geometric entropy, which has nothing to do with geometry, but just the quantum field theory entropy that's there because there's a little bit of entanglement in the ground state. You get that. The entropy in the outside world starts to increase and eventually grows to some size bigger than the entropy inside the box. That's the second law of thermodynamics. But the entanglement entropy must be smaller than both. And if we take as a cue Don Page's calculation, which I will do, this has not been proved in the context of thermal systems, but I'm going to assume it anyway. Oh, the idea that the entanglement entropy is smaller than either of these is definite. That's a theorem. But that the entanglement entropy follows these closely, and then at the last minute just turns over and goes down like this. That I'm taking from Don Page's calculation. Someday somebody has to do better for thermal systems and show that it really does work this way. But so far as I know, I think that's a likely possibility, that you get very, very close to these curves until they turn over. This time over here, I call the information retention time. It's the time before any significant amount of information appears in the outgoing radiation. And by information, now I've discovered that what I call information is not necessarily what the information theorists call information, although I think they're wrong. I think they do call it the same thing, frankly. I think they just didn't recognize it. But what I call information, well, you'll often read that information is just negative entropy, okay? I hate the idea of negative information. So what I'd rather say about a system is if there's a notion of maximum entropy, the maximum entropy of a system would be the logarithm of the dimensionality of the Hilbert space of the system. That would be the maximum entropy of a completely random thing. I would say that the information is the difference between the maximum entropy and the actual entropy, whether it be thermal entropy or any other kind of entropy. The maximum entropy less the actual entropy is what I would call information. And so over here then, now, most systems, of course, have infinite Hilbert spaces, and so the idea of a maximum entropy doesn't make a lot of sense. I would substitute and say, supposing we know one thing about the system, we know its average energy. Right? We know its average energy. What is the maximum entropy that a system can have if it has a known average energy? The answer is thermal entropy. So I would substitute thermal entropy for maximal entropy and just call the information the difference between the actual fine-grained entropy, or in this case, the entanglement entropy, and the thermal entropy. And you can see that, from this point of view, that information only starts to leak out of the system at this special time here, at this crossover time here. That's what I'll call the laws of quantum information. And I will assume that the laws of quantum information are laws of nature that cannot be violated by black holes in particular. That will be the first law of nature that I'm going to advocate as being sacred. The second law, not the second law of thermodynamics, second sacred law, is the equivalence principle. So let me just say the equivalence principle not in a technical way, in a naive way that I would explain to non-technical experts. They never understand it. The technical experts understand it. But here's a picture. Here's a black hole. Equivalence principle applied to black holes. A very large black hole. Let's think about an extremely large black hole. An extremely large black hole, let's think of a black hole whose radius is 10 to the 9th light years. Okay, it's a tenth the size of the whole universe. The radius of the curvature components at the horizon are very small. The actual invariant curvature components, the curvature invariants are very small, and in fact, they're about equal to 1 over the Schwarzschild radius squared. So if the Schwarzschild radius is 10 to the 9th light years, the components of curvature invariants at the horizon are extremely small. And that means, according to the equivalence principle, that all physics that takes place near the horizon should resemble extremely closely the physics of flat space. So, in particular, if an observer is falling into the black hole, the equivalence principle tells us that that observer simply goes through the horizon until they get near the singularity, without anything interesting happening. And in particular, the observer doesn't bump into any obstruction, doesn't see any signs, doesn't hear any whistles. Nothing happens at the horizon that wouldn't happen in flat space as far as that observer is concerned. That's a second principle. It's the equivalence principle, and I also take it as sacred. Let me come back to this law over here and say what it would seem to say, and I think does say, about that same observer, except being watched from the outside. This equivalence principle here applies to an observer who falls through the horizon. Right? It doesn't apply to observers from the outside, because observers from the outside actually see non-invariant components of the curvature, which are very large. But the curvature invariants, the ones seen by the inflowing observer, the proper curvatures seen by the inflowing observer, are very, very small. What would this picture say? This picture would say something totally different. At least if I add it together with the idea that at the surface of the horizon there is a temperature T, which is equal to 1 over 2 pi times the distance from the horizon. That was another calculation that we did, that the temperature grows extremely hot as you approach the horizon. It replaces the heat, of course, that's there in the bomb. What this picture would say would seem to be completely different. It seems to say that the observer falling into the horizon, as he gets near the horizon, the thermal radiation and gets radiated back out encounters a region of enormously high temperature. Encountering a region of enormously high temperature will disassemble its bits, turn them into hot, whatever it is when systems get extremely hot, and radiate the bits back out eventually as information in the Hawking radiation. So these two pictures look incredibly different. And keep in mind, we're talking about distances on scales of 10 to the 9th light years. According to one picture, this observer survives for 10 to the 9th light years, or years, without anything interesting happening. According to this picture, as seen from the outside, just before hitting the horizon, disaster happens and runs into ferocious temperatures, which destroys it.
Can I ask a question about your equivalence?
Yes?
There's something unique that happens when the observer crosses the horizon, and that's that the signature of the metric changes.
Oh no, oh no, 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 no. The signature of the metric does not change. No, sir. What happens is the R component and the T component interchange, but the signature of the metric stays plus, 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 minus.
Right, just the minus moves to a different.
Yes, but that's just a coordinate artifact.
Right, so my question is,
Yeah.
let's say your observer is a physicist and he wants to do experiments where he's actually trying to determine the location of the horizon.
Oh, that's something you can't really do.
So every time he takes 2 steps forward, he takes 1 step backward as he approaches the horizon. As he crosses the horizon, he finds that he can no longer take that step backward because the radial coordinate is now his time coordinate and is forced to decrease monotonically.
He takes a step backward. He takes a step backward just exactly as if he didn't know there was any horizon there. It's just a step backward, doesn't get any further from the singularity.
So this is what I don't understand, how a radial coordinate, which is now your time coordinate, is forced to move monotonically forward just like time is. We can't move backward and forward in time like we can in space. So when he crosses the horizon and these radial and temporal coordinates are switching roles, can he still, he obviously can't move to increasing R while he's inside the event horizon.
R becomes time-like. It doesn't make any sense to go to decreasing R. Yeah, but he doesn't care what you call his coordinate. His coordinate, he still sees just ordinary stuff.
Okay, so from his perspective,
He just says, you're using funny coordinates
you
inside my
can't
horizon.
climb in the radial sense because that's now his time coordinate. What does it look like for him in terms of time? What can he actually?
Absolutely nothing unusual. He has his wristwatch, he measures proper time, he talks to his girlfriend, they have, no, I won't say they have what they have. They do all the ordinary things that people do. They can even look out. They can even look out the horizon and see their friends and wave to them. It's just the friends it's just that their friends won't see their wave. But to them, they see the outside. The outside doesn't see them. Nothing special happens to them. Absolutely nothing. All the same things you're saying are true in flat space. In flat space, you can introduce a coordinate, which you can call R, which decreases as you come in, and then suddenly makes a right angle turn and goes over here and becomes time-like. But it in no way influences anybody who falls through the light cone. It's just a very funny change of coordinate. That was the discovery, if you like, of Finkelstein and later Kruskal and so forth, that it was just a pure coordinate artifact that anything happened about the horizon. Would have no implications from the point of view of the proper measurements made by somebody falling in. So equivalence principle says this. Laws of quantum information seem to say this. They seem like they're contradictory. Let me formulate one way out of the contradiction and then tell you what's wrong with that. Here's the idea. I mean, you could call this a stupid idea, and I think it is a stupid idea, but it's one which has to be dispensed with. Here's the horizon. Let's divide the horizon up into Planck-sized cells, or cells of any size that we like. I remember giving a lecture on this in 1985, and boldly said, let's pretend that each little cell here is a Xerox machine. How do you spell Xerox? Z-E-R-O-X. There's a Xerox machine. Okay. And here's going to be the picture. It seems like it's going to satisfy everybody. Everybody will be satisfied. Any bit of information that falls onto the horizon over here is immediately Xeroxed. It's Xeroxed, and one version of it is radiated back out so that anybody on the outside sees no loss of information. On the other hand, the other Xerox version of it just falls freely through the horizon and eventually hits the singularity. If that's the case, everybody's satisfied. The person who goes through the horizon sees himself just passing through the horizon, doesn't realize he's only a Xerox version of something. The person on the outside sees the same information. Of course, that information may first fall back to the horizon, get scrambled many times, but ultimately in the Hawking radiation, that information would come back out. So that's the Xerox solution of puzzle that's been expressed here. Okay. Now, I gave that example merely as a straw man to kill it, because as every quantum information person knows, that violates a basic theorem. I called the theorem the quantum Xerox, the no quantum Xerox principle. It was 1985. I think shortly before that, the information theorists had concocted something called the no cloning theorem, which is basically the same thing. So I'm going to explain to you why quantum information cannot be cloned or why it cannot be Xeroxed. Probably most of you know. Does everybody know? How many people don't know? Oh, really? Okay, well, I will tell you why. It's very, very, very simple. Suppose we have a machine, and the machine had one import and two outports. And whatever you put into A, two A's come out. Whatever you put into A. And A can be quantum objects, quantum information. Let's prove that such a system violates the laws of quantum mechanics. So let's come over here and prove it. Let's take a very simple system. A consists of a spin-up. All right, the quantum information, the quantum Xerox machine, if it exists, would produce two upspins. This really stands for the tensor product of two upspins, but I don't feel like writing tensor product every time, so I'll just write two upspins. If the spin is down, it will produce two downspins. All right. What if the spin is pointing to the right, along the x-axis instead of the z-axis? Well, if it's a true quantum Xerox machine, then it has to produce two spins pointing to the right. But that's forbidden. Why is that forbidden? That's forbidden because a spin pointing to the right is a linear coherent superposition of up plus down. That's what this means. I'm not going to bother writing square roots of 2. Up plus down, according to this formula here, must evolve as it goes through the quantum Xerox machine into the tensor product of two identical things like this. So that means up plus down, tensor producted up plus down. And that has 4 terms. It has up, up, it has up, down, down, it has up, down, and it has down, up. On the other hand, the linearity of quantum mechanics tells you that if up and plus down passes through the quantum Xerox machine, all it can produce is the linear combination of up, up, and down, down. It's the linear evolution of quantum mechanics. If up evolves to this, and down evolves to this, then up plus down will just evolve to up, up, plus down, down. And the cross pieces will be missing. And that's the theorem of quantum mechanics. I mean, it's not much of a theorem. It's an important observation, but it's not a very hard theorem to prove. And so quantum information cannot be cloned. Quantum information simply cannot be cloned, or it cannot be Xeroxed faithfully. And that's a, okay, Robert, does that make you happy? Okay. All right, what does the principle of black hole complementarity say? I'm going to say it very simply. It simply says, no observer sees or detects a violation of the laws of nature. The laws of nature being the laws of quantum information, the laws of the equivalence principle, and the law of no quantum Xerox machine. That's really part of the laws of quantum information. Right? But we really do seem to have some kind of clash. Let me rephrase what the first principle says here. I hate writing things on the blackboard. I'm simply going to say it. From the first principle, applied to black holes now. Applied to black holes, what it says is that from the outside, a black hole horizon, or maybe we could call it a stretched black hole horizon, consists of a hot, temperature 1/2 pi rho, a hot collection of degrees of freedom that absorb, thermalize, that means scramble, and re-radiate all the information, including whole observers that might fall onto the black hole horizon. In other words, it says in words that the black hole consists of a hot environment full of entropy. I mean, we know it's hot because we do this calculation. Full of entropy, we know what the entropy is, we know what the temperature is. It must say that there are degrees of freedom which absorb, thermalize, and re-radiate any information that falls onto it. That's what the rules of quantum information would say. What does 2 say? Well, 2, the equivalence principle, says that an observer falls freely through the horizon with nothing happening to him. Number 3, no one can ever detect duplicate information. Those 3 principles are regarded as sacred. They sound inconsistent, but I don't believe they are. So let me explain to you why I think observationally they're not inconsistent. The 2 views of black holes here, I think of as complementary in the sense of Bohr. Now, nobody could ever figure out what the hell Bohr meant when he said complementarity. I'll give you an example of complementarity. What complementarity means to me is the substitution of 2 very short words, one for the other. The words are and or. For example, in classical physics, a particle has a momentum and a position. In quantum mechanics, it has a momentum or a position. You don't try to measure both. You don't represent the state of a system as a point in phase space and a point in x. You represent the state of the system as a probability distribution in P or a probability distribution in x. Depending on the experiment that you do, one aspect or the other might be important, or one aspect or the other might be revealed. That's what I mean by complementarity, the substitution of the word or for and. There is information inside the black hole, and there is information outside the black hole. There is information inside the black hole, or that information is outside the black hole, depending on the way that you look at it. Let me go a little more with the analogy with X and P. And let me remind you about Heisenberg's microscope, because we're going to use Heisenberg's microscope to analyze some of the things that go on near the horizon. Let me just remind you what it was that Heisenberg said, because I think it is important to remember. When it came to X and P, the uncertainty principle sounded a little bit, first of all, on the face of it, it sounds inconsistent. If a particle can have a position at every instant of time, then all you have to do to find its velocity is subtract its position at 2 instants of time, and you know its velocity. So, as you well know, all of you, Heisenberg thought about this as a Gedanken experiment and said, how could you measure both the position and velocity of a particle? and found out that there was a contradiction. And the contradiction in measuring both of them, or that there was no contradiction in the assumption that you couldn't measure both of them, he said, how do you measure the position of a particle to a given accuracy? You shine photons on it. Well, photons are discrete. This was the new thing, that photons were discrete, and the minimum number of photons that you could hit something with was 1. All right? If you want to see that object clearly, you have to use a short wavelength photon. These lines are just supposed to be the wavefronts of the light ray. And the more accurately you want to see the thing, the bigger the photon energy that you need, and the result is a random kick. And that random kick changes exactly the thing that you would have liked to measure next, namely the momentum. So the measurement of one thing, this is what complementarity means to me, the measurement of one thing precludes the subsequent measurement of the other thing without having disturbed the system badly enough to completely ruin the second experiment. So that's what I mean by complementarity. Of course, you can ask exactly the same thing about trying to measure momentum, and you always find that measuring momentum destroys the information about the position. I want you to keep that in mind when we start asking questions about black holes, which I think it is central to the whole story. Thinking about Gedanken experiments and trying to see if there's something is there really something inconsistent about these two pictures, or are they just the two complementary pictures that are surprisingly consistent with each other? I'm going to do some examples of some simple Gedanken experiments to show you how they work. The first one, and these are old things. They've been known for more than 15 years, but I'm not sure that they've been thoroughly absorbed into the consciousness of black hole physics. I want to ask the first question is whether baryon violation takes place at the horizon of a black hole. Why should it? Well, it should, because the horizon of the black hole gets arbitrarily hot. As you get close enough, or I'm assuming, of course, that we're talking about a theory where baryon violation is part, some grand unified theory. For example, here's a model. In the model, a proton can have a transition to a positron and another object that I'll call X, a boson that I'll call X. This is a simplification of what happens in grand unified theories, but you can also have, this wouldn't in itself violate baryon number. It would simply tell you that X have baryon number 1. Okay? But then there's another vertex in the same theory that E plus goes to E plus, also emitting an X. This tells you that X has baryon number 0. Can't have both 0 and 1, and so with both these vertices in the theory, baryon number has to be violated. Okay, now I'm going to assume the X boson is very heavy, as usual, and ask what is a proton? Well, a proton, of course, if looked at microscopically and looked at very short times, consists of a series of transitions: proton, electron, X boson, proton, electron, X boson. My assumption is that the X boson is very heavy, but I'm also going to assume that the dimensionless coupling constant that appears here is order 1, is not very small. The heaviness of the X boson should protect the proton against decay, of course. So a proton is a perfectly good thing. It has a transition rate of order 1 to an electron and an X boson, but the X boson is so heavy that we never see it. So that's what a proton looks like. You can ask the question, what is the percentage of time that the proton spends with the wrong baryon number? The wrong baryon number means now that it's E plus X instead of proton itself. You might think that the answer is very small, and the answer is not very small. The answer is of order the square of the coupling constant. You might as well, for the purposes of this calculation, think of the proton and the positron as essentially massless. In that case, the only mass scale in the problem is the X boson mass scale. You can call that 1 if you like. So there's no large number in this problem because the coupling constant is also order 1. If you work it out, and it's a matter of what it really comes down to is working out the wave function renormalization of the proton, the wave function renormalization of the proton is more or less about 1, which means that the proton has a probability of order 1, actually of order g squared over 4 pi to be exact, to be an electron, a positron, and an X boson. So it's not that the case that the proton has a very small probability of having the wrong baryon number. What then do we actually mean by observable baryon number? What we mean is the time averaged baryon number, averaged over a period of time, long by comparison with these oscillations. That is what we mean by ordinary baryon number, the time averaged baryon number averaged over many of these oscillations. That is the thing which is hard to change, the time average. Okay? So that's something to keep in mind. Now let's imagine a proton falling toward a black hole, in particular falling toward a black hole horizon. Here's the black hole horizon.
By the time average, then you mean at the time average over the mass of the X?
Over a time scale longer than the mass of the X. Right. Right. You know, for our purposes, it could be a time average over a lot longer than the mass of the X. Right. Right. That's what I mean. Yeah. Another way of saying it is if I took a very, very rapid snapshot of the proton, I would have a relatively likely likelihood of finding it with the wrong baryon number. If, on the other hand, I have a very long shutter speed, if my camera has a long shutter speed, it'll average the baryon number over many such oscillations, and that's what we call baryon number. All right, now, let's think of a baryon falling through a black hole horizon. And it's doing its thing. Somebody falling through it with it sees nothing unusual about that baryon number. They follow it through. They do whatever experiments we do on baryons. They average the baryon number exactly like we average the baryon number. But what about somebody on the outside of the black hole? Somebody on the outside of the black hole watching this. Right? Somebody on the outside of the black hole gets to see this process slow down by time dilation. As the proton approaches closer and closer to the horizon, the outside observer sees it slow down and slow down and slow down. Maybe some percentage of the time, as the baryon goes through the horizon, it's caught in the wrong state. Well, from the outside perspective, that wrong state lasts for an infinite amount of time, because remember, Schwarzschild time looks like this. So from the outside observer point of view, baryon violation, which lasts forever and ever, has occurred right at that point over here. So the key to a lot of these puzzles is the understanding of the difference between physics seen with a slow shutter and a fast shutter in a camera.
What
Yeah.
you say operational, will he
Right.
live so long?
Who lives so long?
Will the observer live so long to detect the consequences of the slowing down of the oscillation of the virtual graph?
Remember, this observer can be far outside the black hole, so he's not subject to large acceleration. If you're worried about
When
it,
he gets to the message, that message is skimming along the light cone, and
Yes.
he's going to get the message when he's along the light cone. So he has to wait an awful long time also to get it.
well, the message you mean,
He has to wait.
Robert.
Okay.
What you mean by the message is wait for the Hawking radiation to report what happened. I don't think there's any.
When I'm
Which is
putting it
true.
in my mind, I'm comparing how long he lives
Yes.
with how to get that message.
Yes.
Due to the slowing down that you're talking about of the composite near the horizon. I'm comparing two times.
No, this happens, this happens extremely fast. The slowing down happens extremely fast. Let me explain why.
For him.
For the outside observer. No, for the inside observer, nothing slows down. Yeah, let me explain why. What I calculated previously was, from the outside point of view, how the momentum of the chalk changes with time, okay? And that is that the momentum goes like e to the t over 4mg.
I guess my question isn't clear to you. In order for him to get to a delta rho, which is so small,
Yeah, it's fast.
this is a very important effect, he has to wait a long, long time.
No? Who has to? Him?
Yeah.
No. No. Here it is.
If I throw a can of tomatoes,
It's t log, it's m log m. He has to
he
wait.
has to wait a long, long time.
M log m. M log m. Where m is the radius of the black hole. M log m. The momentum increases this way. The time dilation follows the momentum. And so there's an exponential increase of momentum as you fall toward the horizon. All right? And the time that you have to wait until you see, it's very fast. It's the same amount of time that it, roughly speaking, took the electric charge to spread over the horizon.
Yes, I don't understand. Because if you throw an object towards a black hole, for you, outside, you'll have to wait almost an infinite amount of time before it starts to snow.
You have to wait an infinite amount of time
Before that happens, for you.
No, no, no. You have to wait an infinite amount of time before it actually passes through the horizon. Okay? But
And so
let's,
we have to compare.
no, that's not what we're comparing. We're comparing something else. We're asking how long a time does he have to wait until he sees that proton enter into the region where the temperature is the gut temperature.
The order of NX, yeah.
Yeah, that's a hyperboloid like this. That's a hyperboloid like that.
That's right.
All right? It has a certain distance here, which is some gut scale. All right? The answer is not very long. It's very short until actually, because of this exponential growth. Okay? It's true. It doesn't take long to see something hit the stretched horizon. It's the distance between here and here, which takes forever. All right? So, no, it doesn't take very long to see the thing enter into the region where the temperature is big enough to cause this transition. Okay? Now, okay, so does this really happen?
Yeah.
Yeah.
So, is he actually seeing a violation of average baryon number or just an increase in the fluctuations? Because, the way you described it is a time dilation effect. You'd think that, say if you have
Well, there's only one
lots of
proton. There's only one proton.
Well,
We're going to talk about looking. We haven't actually looked yet. We've only drawn a picture. But now we can talk about actually looking and trying to see what the baryon number is at this point. So we need an experiment. We haven't done an experiment yet. Right? One baryon number. There's no question of fluctuations or no question of probabilities anyway. But just the question is, what happens if some observer tries to observe this proton and to see whether it was really an electron, a positron, plus an X-boson, or was it a proton? The observer who falls through sees a proton because it doesn't have the time resolution to see the fluctuations, to see these events taking place. Okay, so let's imagine then a Heisenberg experiment to try to see what's going on extremely close to the horizon over here, or rather within this distance here, within which the temperature gets to be of order temperature graph. So here's the experiment. And the kinematics of it is not too hard. I won't even bother going through the details of the kinematics of it. You can more or less see what happens. Here's the region where the temperature is greater than T gut. The proton falls through. And what we're going to do is illuminate this region over here with radiation, which will interact with the proton at this point and send out a message Actually, it can't send it out faster than the speed of light. It has to send it out here. It sends it out to somebody out here and tells them which of the two possibilities were there. All right? So a photon has to get into the system in a short amount of time. You can't do this experiment with less than one photon. What's going on here, to keep in mind, is that in classical physics, you can get information with an arbitrarily small amount of energy and an arbitrarily small kick. But in quantum mechanics, you have to use at least one photon to get the information out. That photon has to be able to get into here, into this region, in a time scale, let's call a proper time scale tau, which is of order 1 over the temperature. In other words, another way to say it is that this proton in its own reference frame, has a very small amount of time during which to be measured. If it's going to be measured, it has to be measured with a very high frequency photon. And in fact, if you work it out, basically that photon has to have, or the time scale here is of order 1 over t gut. That's how much time you'll have to do the measurement. If the photon is going to get into there with certainty 1 and send out its message, the energy of that photon has to be bigger than or equal to t gut. Well, if the energy of a photon that you hit a proton with is bigger than t gut, guess what it will do? It will have the effect of causing the proton to decay. If you hit a proton with a photon of order t gut, then with a probability of order 1, it'll cause the proton to decay. So it's exactly like Heisenberg's situation, where the thing that you're trying to confirm, in one case, the velocity of the particle, in the other case, the fact that the proton hasn't decayed, is itself caused, or is itself intervened with by the measurement process, causing the thing to happen, which is exactly what you were trying to prove doesn't happen. Right? It's a perfect case of what Bohr called complementarity, that you cannot, by these kind of measurements, infer that the proton didn't decay at the horizon. Any attempt to try to detect that the photon went through without decaying will cause the photon to decay. That's one Gedanken experiment. I'm going to go through a couple of them.
So what exactly are the two complementary observables here?
Sorry, I can't hear you.
What exactly are the two complementary observables here?
Well, I wasn't exactly thinking of it in terms of two complementary observables. What I was just imagining is that the thing which you're trying to confirm the thing that you're trying to confirm is this itself severely disturbed by the, I don't know, that's an interesting question to try to formulate it in two complementary, I'm not sure. But the logic is that the thing that you're trying to confirm, namely that the photon did not decay before it went through the horizon, is itself upset, or how to say it, is intervened with and caused to happen by the measurement itself. You're right, I should think about, we should try to formulate it in terms of an uncertainty principle. I haven't thought about it very hard in that way. Let me come to another Gedanken experiment. Can you ever detect a quantum Xerox machine? Can you ever detect a quantum Xerox machine? The question in this form was first formulated, to my knowledge, by John Preskill in 1993. He asked me about it. And the idea went something like this. Here you have your black hole. Well, let's see, do I want to draw it that way? Let's just draw it. Let's begin by drawing the black hole. Just as a light cone. So, here we have the horizon of our black hole. What's down below here is not very important. I'm not interested in it. Here's the interior of the black hole. Here's the exterior of the black hole. Hawking radiation comes out along here. It looks like it hugs the horizon, but of course it doesn't. The metric is such that the Hawking radiation is really departing from the horizon, but in conformal coordinates, one winds up drawing the Hawking radiation as if it were hugging the horizon. And here's the game. We're going to throw in a bit of information of some sort. Here it goes. Now, according to the equivalence principle, the bit of information just flies in, goes over to here. On the other hand, an external observer is going to stand outside and collect information out of the Hawking radiation. If the principles of quantum information are correct, then after a time, an appropriate time, it should be possible to collect that bit of information in the Hawking radiation. So he waits long enough, collects in his shopping bag the bits of information that corresponded to the infalling bit over here, and once he's got it, he jumps into the black hole. Jumps into the black hole. There's not much danger of seeing information duplication outside the black hole because there's no way that this bit can get out. But what about seeing information duplication inside the black hole? So now there's two bits of information which are really supposed to be the same bit. The clone of this bit over here as seen in the Hawking radiation, and we now have a problem. Because what if, just after passing the horizon here, a quantum teleportation of this information would teleport it over to here, for example, by a photon. Then, behind the horizon, an observer over here would have detected a quantum duplicator. Okay? Sounds like we might be in trouble. Resolution. What is the resolution of this paradox?
How did the first guy get the information? Because of the scatterer? Because of the scattering?
The Hawking radiation.
Against the Hawking radiation?
Yeah, sure. No, all right. The first thing is, there is no violation of causality in saying that information from here gets out to here. After all, this is in causal contact with this point. So you could say, yes, the Hawking radiation carried it off, brought it up to here, that's the assumption. And now we have two bits, which are supposed to be the same bit, and we have the potential possibility that somebody at this point will discover the quantum cloning of information from over here and from over here. Is there...
Let's imagine you. There is this red matter, it's very heavy particles,
Okay.
more than the planet mass, yeah?
Okay.
And
Sure.
also the particles which absolutely do not interact with anything, but just gravitation. Then this kind of Hawking radiation which you draw,
Yeah.
will not fill these particles. And how then I should think about this situation? In principle, nothing will change these equations.
Look, what happens is as this particle falls into the black hole here, as it gets closer and closer, the interaction energy between the Hawking photons and this thing grows exponentially.
You mean gravitational interaction, which is inevitable, also
Among other things, every interaction, but in particular the gravitational
So it
interaction.
means that gravitational interaction...
If nothing else, gravitational. Yeah, if nothing else. Okay. Okay. But I'm following some principles, which means I'm making some assumptions.
But when you do that, of course, when you get very close to the horizon, you have to question whether your picture based on free quantum field theory is okay.
Absolutely. But the point is, we're going to find out that it's not only not okay, it's not okay in a tremendously big way.
Yeah.
We're talking about huge distances now.
Right.
Right. So it's not just that quantum field theory is breaking down at the Planck scale. Something is breaking down on enormous distance scales. That's what we want to grapple with. But let me show you what the resolution of this paradox is. The resolution was partly the paradox came up during a conversation with John Preskill and Don Page. Had I then left the room and gone away, Don Page and John Preskill would have very quickly resolved it. John Preskill had half the solution, Don Page had the other half, but Don had to go to the bathroom, he had eaten 3 big desserts, and I had to call my wife, and John Preskill wanted to go to the next lecture. So it took a little bit of time to sort this one out. Okay, so here's the resolution. And the singularity plays a fundamental role. Singularity is up here. Okay. In fact, I probably should just use this diagram over here. The first thing is, which was taught to me by Don Page, is this idea of information retention time. It takes an amount of time of order t of order n cubed g squared, that does have units of time. There's some speeds of light in there, which I don't remember. It takes that much time to retrieve a single bit. That's how long it takes for half the entropy to leak out of the black hole. So this point cannot occur until rather late. Okay, when it's rather late, we then send in our observer, but that observer is going to eventually hit the singularity. Now, there's a long, long time before it hits the singularity, but in these coordinates, in these Kruskal-type coordinates, let's call this coordinate u. In Kruskal coordinates, the coordinate distance here is obviously very small. The longer it has to wait to jump in. So this Kruskal coordinate, the light cone Kruskal coordinate, which is called u, how big is it between here and here? Well, everything gets exponentially squeezed over here. Everything gets exponentially squeezed over here. It's easy to carry out. And the answer is delta u is of order e cubed e to the minus n e to the minus t. Let me look it up. E to the minus m squared g. Everything gets shrunk. In other words, if I plug in that I have to wait this long, and then use the properties of the Kruskal diagram where everything gets shrunk up over here, I find out that this delta u over here is very, very tiny, e to the minus m squared g. Well, I now go back to over here and follow a photon backward from the point where this guy hit the singularity. And I ask, how much time does he have to send the signal? How much time does he have to send the signal, the quantum teleportation signal, from here in order that it can be intercepted by this observer before being destroyed at the singularity? The answer is also e to the minus m squared over g, e to the minus m squared g. Now, this is a disaster, because if this guy is going to have a clock which tells him to send, or if he's going to be able to send out a photon in that short a time, that photon, that single photon, has to have an energy which is at least as big as e to the plus m squared g. Well, that's crazy. There's no possible way that a system with that much energy can possibly fit into a black hole of mass m. So there's no way that this experiment can happen. By an enormous factor, an enormously large exponential factor, the signal cannot be sent out, or equivalently, this guy cannot be turned around and brought to intercept the collector over here, who collects information and then jumps back into the black hole. It will always crash into the singularity long before that signal can be sent or received. So, nobody will ever see, by this method, quantum information duplication. Again, a kind of Heisenbergian argument. Note that the singularity plays an important role. The singularity plays the important role of simply terminating the point at which he can collect information. Okay. I'm going to give you another example. And the other example tells us other kinds of information, very interesting information. The other information is what I'll call atomic diffusion at the horizon.
But really, on the other side, if everything here will be encoded in Hawking radiation, which will come out,
Yes?
then you have to see this kind of
What's that?
outside.
Say it again?
You see, you have this kind of thing, right?
Yeah.
For falling in the black hole.
Yes.
When you are inside black hole, then there is no actually any danger because not enough time
Yeah.
to exchange by signal.
Right.
But as you said, everything should be encoded in Hawking radiation. So show Hawking radiation, which is possible to the horizon, should know about everything actually what happened
Right.
or what will happen.
Right.
So in outside world, you could have to see this kind of duplication.
No, you can only see duplication by seeing both of them. You can, seeing duplication means seeing both of them. All right. Oh, look.
You see, not outside, but already inside.
We can't see duplication outside because this bit can never get back out.
Yeah.
We've now discovered we also can't see information duplication inside. Now, what I'm doing now is not trying to find a mechanism for explaining how the information gets out or anything else. I'm trying to test a set of ideas, a set of principles, and see if they run into operational trouble, to see if they run into operational inconsistencies, if you like. So far, no inconsistency. Let me give you another one. This one's kind of interesting because it tells us another kind of information. There's my horizon now. And sometimes I'm going to freely pass from one kind of picture of the horizon to another kind of picture to yet a third kind, assuming everybody can follow me. Here's a horizon, black hole, an atom falls onto the horizon. Following the atom just goes right through the horizon. Nothing happens to it. An atom is 10 to the minus 8 centimeters. This black hole is 1 billion light years in diameter. The little spot is left on the horizon over here, no bigger than 10 to the minus 8 centimeters. Or it corresponds to a little spot on the horizon that big. That's the picture that somebody falling through the horizon. Of course, the person who falls through the horizon never really sees the horizon. They simply see the fact that the atom is never bigger than 10 to the minus 8 centimeters. Now, somebody on the outside, what is the consistent picture that they have to be able to see? Well, the horizon heats up. An atom falling into a hot horizon will eventually ionize. The electron will get pulled out of the atom. If it gets hotter, the nucleus will break up, the nucleons will break up, and of course, being subjected to all of this very, very intense heat, we know what will happen to them. They will diffuse over the horizon. Anything subjected to that kind of heat will get scrambled. It's got to be like a drop of ink falling into very hot water that's going to diffuse. It's got to in fact, it's got to thermalize. It's got to come to thermal equilibrium eventually. And in thermal equilibrium, that little drop of ink is going to be spread and make just a little bit of gray water. So what we should expect on the basis of this kind of high temperature behavior near the horizon is that from the outside point of view, something completely different is seen or deduced, if you like. Namely, that this atom, when it gets close enough to the horizon, ionizes, and after it ionizes, it begins to diffuse, and eventually its bits of information are diffused and scrambled over the whole horizon. So the atom undergoes a traumatic disruption, and that happens quickly, incidentally. Remember, I showed you how long it took a charge to diffuse over the horizon. It was m log m. The same thing here. It would take about a time of order m log m. That's 1 billion years, but what's 1 billion years between friends? And within that relatively short time, the atom must spread itself over the whole horizon, every bit of information. So again, what looks like a contradiction. again, we go back to Heisenberg and we say, what would Heisenberg do? What did Heisenberg do? There were some things that Heisenberg did do that we won't talk about. But what would Heisenberg do under these circumstances? He would get out his trusty microscope and illuminate. Well, let's go back to this picture. He wants to confirm the picture that says that nothing happens to the atom. So he takes out his trusty microscope, he illuminates that point, as well as that point can be illuminated, sends out a signal, and the eye in the sky sees the signal and reconstructs from the signal what it was that happened to the electron as it fell through. Now, Heisenberg has a tremendous advantage. As this gets closer and closer to the horizon, obviously he has to use shorter and shorter wavelengths. Shorter and shorter wavelengths might not have been very good for studying baryon decay because it would blast the hell out of the baryon. But if you want to see high precision location, all we want to do, we don't want to measure its velocity. All we want to do is measure its location after a certain time. A very high frequency photon you would think is very good. We think it's very, very good to use a very high frequency photon, scatter it off there, and under those circumstances you should be able to see with great precision that this electron passed through the horizon in a very narrow region. Okay?
Sorry.
Yeah.
So when you say a high frequency photon, I mean, the photon's also experiencing some kind of blue shift as it falls in. So you're talking about the energy from the outside or the energy when it actually hits the atom?
Well, the answer doesn't matter much, because the momentum of this thing is increasing exponentially, and it's power laws versus exponential, so it doesn't really matter very much. But it is a good question, but let's just say high frequency from the outside. That gives us plenty of room, because that means it will be very high frequency when it gets here. Okay. Well, we're making some assumptions about what happens.
You have an electron?
Mm-hmm.
It's an electron now going through.
Yeah.
Because it began as an atom.
Oh, it doesn't matter. Sorry, excuse me. Atom, electron, who cares? Yeah.
It isn't because...
Atom.
And we want to see if it spreads apart the way you do.
Yeah, we want to see whether it spreads apart. Good. So we send in wavelengths, which are... now, as this gets closer and closer to the horizon, we're going to have to, not because we want to see distances smaller than 10 to the minus 8 centimeters, but because we have a very short amount of time to see it, we have to use higher and higher frequency photons. Well, that doesn't sound like any problem, because high frequency photons are good at localizing objects. So that sounds like a benefit. But it's making an assumption about what happens when very, very high frequency objects collide. And incidentally, by the time this gets to about 1 Planck distance from the horizon, well, maybe it's spread out to about 1 Planck distance. But if we keep waiting, then it will spread out a lot. And the time scales are such that in order to see this kind of spread, we would have to use very trans-Planckian photons. You do the kinematics, and in order to see it spread by more than the Planck scale, you'll have to use higher than Planck scale photons. So then the question comes, what do we know about the collision of particles above the Planck scale? All right, so let me begin by drawing a graph about what we know from quantum field theory. Let me put on the vertical axis the distance that's probed, L probed in a collision. What does that mean? It means if I want to see small structure, I use high energy. If I want to probe a certain distance scale, I use a certain frequency. And let's plot here energy. As everybody knows, the 20th century was completely dominated by the fact that this curve looks like this. If you want to probe small distances, you use high energy. Okay? That's what the curve looks like. It's a hyperbola, and it's the relationship between energy and frequency, or energy and momentum. Okay? So this picture would say the higher the energy that you need here, the better you do at probing small distances. This has to break down in order for this picture, in order for this picture of a diffusing particle to break down. But, sorry, for the diffusing particle to grow. It's this that has to break down. But we know that that's going to break down. And here's how we know it. Let's collide two particles at energies below the Planck scale. If we collide two particles below the energy of the Planck scale, we get probe distances which are very small. Now let's probe particles way, way above the Planck scale, 1,000,000 times higher than the Planck scale. What happens? What happens is the small distance structure all gets shrouded by a horizon, by a black hole. Black hole forms. The higher the energy, the bigger the black hole. What happens next? The black hole radiates. And the black hole radiates photons whose wavelength is comparable to the Schwarzschild radius. So the result is that in an attempt to see smaller and smaller distances, once you get above the Planck energy, you get frustrated. Instead of seeing small distances, you start seeing big distances over again. What you start seeing is a very, very fuzzy picture because the photons that are carrying out the information have wavelengths which are growing like the energy. In other words, this curve is guaranteed to go back up. It's going to go back up linear with energy. If you collide particles above the Planck scale, if everything that we think we know about collisions and black holes and so forth is correct, it will tell us that this higher and higher frequency here gets to be worse and worse at localizing these particles. Instead, as the energy goes up, what you get to see is a more and more diffuse picture of what's going on at this point, rather than a better picture. And it is consistent, numerically you can work it out. It is consistent with the rate at which diffusion would take place on the surface of the horizon. Namely, you cannot see clearly enough to see that the diffusion doesn't happen. That's probably the right way to say it. So that's another example of the frustration.
And then how do you know quantum mechanically when you do the quantum field theory that there's time enough that you can think in terms of black hole physics for this hot ball?
Well, this horizon forms.
The
horizon forms in the past. I mean, the horizon forms when they get within, whatever the distance that they. So the horizon doesn't happen fast. When they get a certain distance apart, the horizon happens, and you can no longer see inside it. So what's going to happen is when this gets close to this falling atom, maybe not so close, it's going to get shrouded inside its own black hole horizon, and then the radiation from that is going to smear the image over a large distance. So
you can prove that if you take two Planckian fields, two Planckian packets, collide them, and that
super Planckian, trans-Planckian. Can I prove that? I've never proved anything in my life. Why should I begin now? Well, okay. So here's what
I mean, I know the papers.
Yeah.
Based on string theory.
No. Forget string theory. Forget string theory. There's a classical calculation. There's a classical calculation that can be done for very, very high energy particles. We use Heisenberg sexual metrics to study the collision and see what happens. Okay, this was done for head-on collisions a long time ago by two physicists named Pain and Death. Pain and Death. I don't know, Pain, P-A-Y-N-E, or P-A-I-N? Pain and... Pain and Death did this calculation. And sure enough, they found about, I think I can't remember if it's 30% of the stuff goes off as Bremsstrahlung and the rest remains a black hole, or whether 30% goes into the black hole and the rest goes off as Bremsstrahlung. So yeah, that calculation is done, but it's a classical calculation. But the thinking is when the energies get this high, it ought to be a classical calculation. The gravitational fields get huge due to all that energy. It ought to be a classical calculation. Now, can I prove it? No, of course not. But what we're trying to do is to try to see whether we can escape from a disastrous conclusion, namely the conflict of principles. So this would give us an escape. And since most of the physicists I know anyway think that if you collided two particles at that energy, you would make a big black hole, I would say that that's one of our more or less trusted procedures. Now, it's 5 to 12, and I haven't even really started my lecture today. What I was going to do was talk about what happens as strings approach a horizon. That's even more interesting, and you can actually see this kind of thing happening. I have a little video of it. I'm wondering whether I should... I know that people have to leave here at 12, is that right? Can we go on to 12:15? I'm not sure. If we can go on to 12:15, I would continue. Otherwise, we can...
You can.
Hmm?
You can.
We go on to 12:15?
When the other people, what are you guys doing? You can wait.
He said he'll wait for a while.
What's that?
The driver said he'll wait for a while. He was on the
Yeah, 12:15 is fine. Yeah.
Don't worry, I'll drive you. Right. What I wanted to talk about is the central difference between quantum field theory. Now, we don't have time to do things technically. Many of these things are done technically, and the things I'm going to tell you about next is done technically. It is the basic difference, in a sense, between the pattern. Well, the pattern I'm talking about now is the pattern of seeing things at higher and higher time resolution, better and better time resolution. What do things look like if you were to take a super rapid photograph? Now, you can't take super rapid photographs by any other known means except by looking at them as they approach a black hole. Everything slows down in the black hole, and so you get to see what otherwise would be very rapid oscillations. But what does physics look like mathematically? What's the mathematical pattern of information or structure or whatever in quantum field theory? Spatially, how does it look? And how does it look in string theory? The answers are extremely different, even in free string theory. Extremely different. So different that you begin to wonder whether string theory is anything like quantum field theory at sufficiently high energy or at sufficiently small time resolution. First of all, what does quantum field theory look like at high time resolution? High time resolution means a fast camera. All right, so rather than go through the renormalization group arguments, the ones that Kogut and I made many years ago that are also called the Altarelli-Parisi equations and so forth, which tell you how things resolve as you look at them on both faster and faster time scales and with better and better microscopes. I'll just give you pictures. Right? And the picture I'm going to give you is for a scale invariant quantum field theory. Roughly speaking, here is the pattern. It's what I call the Russian doll pattern, quantum field theory. Things inside things, inside things, inside things, in a scale invariant way, down to infinity. So I'll just draw that in the following way. We have some structure. When we don't look at it too closely, it looks like a blob. When we look at it more closely, we discover that it's made of 3 blobs. I didn't particularly here have in mind the proton and its quark constituents. And when I say 3 blobs, it could also have 4 blobs sometimes, or 2 blobs sometimes. You look at it with a better time resolution. Incidentally, why do you need both time resolution and microscopy? First, go back to an atom. In an atom, the electrons whiz around the nucleus, and no matter how good your microscope is, unless you have fast time resolution, you won't see the electron. You'll just see a cloud of electrons. No matter how good your space resolution is, you've got to have time resolution also to be able to see that instantaneously the thing is a proton and an electron. So you get good enough time resolution, good enough space resolution, you see that an atom is a proton and an electron. All right? You do the same thing with a nucleus and you discover that it's protons and neutrons. You do the same thing with a proton and you discover that it's made of quarks. You do the same thing with quarks. Well, I don't know what we're going to find, but if the theory is a conformal theory, if it's a fixed point theory, we will find the same kind of things inside. And this will go on indefinitely. Smaller things inside smaller things in a scale invariant way. That's the pattern that I call the Russian doll pattern, and it's the basic pattern of quantum field theory. Notice one thing, that as the time resolution gets better and better, the whole object doesn't grow. It just develops finer and finer structure. If I wanted to talk about what happens at a horizon, all right, here's my horizon. An object in quantum field theory, this object is now meant to have some extension, and I'm now doing quantum field theory in a fixed background. Here's my game. If I were to draw lines of constant time, lines of constant omega, if you like, well, they look something like this. But very close up here, they're just a series of parallel lines, and they accumulate in sort of a scale invariant way as you get closer and closer to the horizon. 1 unit of omega occupies a certain distance. The next unit of omega, half the distance. The next unit of omega, half the distance, and so forth and so on. And so ordinary time, as seen by a Schwarzschild observer, pretty much looks like light cone time, except light cone time that is chopped up into smaller and smaller bits. All right. So, in particular, if this object falls through, and you ask how is it seen if averaged over a little bit of Schwarzschild time, that means a little bit of omega, it'll correspond to a faster and faster shutter speed. Why? Because before it passes through the horizon, you have less and less time. So if you're going to look at it between the time that it's outside and the time it goes through the horizon, you have to divide it up into smaller and smaller time intervals. And so what you would expect is to see this pattern. And how this pattern looks is with each interval of omega, the particle might split into two. Each time it splits. Each time it splits. Into 3 in this picture, but in this picture only 2. And as you look at it from a great distance, as it approached the horizon, you would see it break up into smaller and smaller constituents, which would have this nested pattern, but it wouldn't grow, and it wouldn't grow in the perpendicular direction either. Remember, the horizon direction is perpendicular to this. It would just get smaller and smaller substructure. This is not what we need if we want to understand how this diffusion over the horizon takes place. Instead of seeing a diffusion, what we see is smaller and smaller substructure with the thing passing through the horizon having a fixed size. That can't be right. That can't be the right picture of what goes on at very, very, very small time intervals. So let me tell you what happens in string theory. The picture is very different. And
you haven't taken into account that for photon, that the vacuum fluctuations in the field, and the collision to the vacuum fluctuations with that structure, and that can spread out in quantum field theory.
What can spread out? Oh, you mean, well, that's what these things are. That's what they are. They are the vacuum fluctuations. Here's our basic object. It splits off things. Things split off other things.
But in the presence of the horizon,
there is no horizon. It's empty space. It's just empty space.
The horizon of the black hole,
Mm-hmm.
and the quantum fluctuations as you said yourself, the apparent energy becomes enormous and the gravitational interaction.
Wait. That's only if you try to, no. That's only if you try to probe it with something.
Say it again?
That's if you try to probe it with something. The horizon we're assuming is just pretty much empty space. So the first question is, what would a conventional quantum field theorist see in empty space in Ringler coordinates, if you like? That's the first question. All right?
Okay, well,
All right?
even that, an accelerated observer, what kind of photons will he see when he accelerates so that another guy observes him?
Wait. Good. So far, I'm not even doing an experiment. I'm just talking about a mathematical description of a particle. You're asking about vacuum fluctuations. Well, vacuum fluctuations are part of the structure. If they connect to the particle, they're there. There are other vacuum fluctuations which are out here. But the main pattern, the point is the pattern is that there's no sense of growth of the particle. There's no sense of growth of something as it passes through here. In empty space, in ordinary empty space. Right? What I'm going to tell you is that string theory is extremely different. That is not the pattern. The pattern is not the pattern of Russian dolls. It's the pattern of what's called branch diffusion. Branch diffusion, or branching diffusion is the correct term. First I'll tell you what branching diffusion is, and then I'll spend a minute or two deriving it from the simplest principles of string theory, and then show you a video that shows you actually a Monte Carlo simulation of how a string falls through the horizon. In free string theory, in purely free string theory, with no non-perturbative corrections. Non-perturbative corrections are important. Okay, let me tell you first what branch diffusion is. First of all, what's non-branch diffusion? Non-branch diffusion is you take a point and you let it random walk, and then you let it random walk, and you let it move in random directions, and eventually it moves to a distance which is the square root of n. That's diffusion, ordinary diffusion of a particle through a hot material. Branch diffusion, or branching diffusion, is the following pattern. You start with one particle. It splits into two, it branches, and they move off in opposite directions by a certain distance, which we'll call Ls for L string, but it's the basic random walk distance. This one disappears and is replaced by two separated by L string at some random angle. Next, each one of these splits into two at a random angle. Same separation. And what we're left with now is 4. Keep this going. Every interval of time, let it branch, let it diffuse, remove the old ones, put back the new ones. That's called branching diffusion, and it has the following property, that if you calculate how big the whole thing gets, it gets as big as ordinary diffusion. In other words, a ball of stuff has a size which grows like square root of n, square root of the number of steps. Why is that? Well, if you just follow any one of the paths, any one of the typical paths is just an ordinary random walk. Okay? So it grows relatively square root of n. On the other hand, how many particles are there in the end? The number of particles in the end is 2 to the nth. So they get extremely dense. They get extremely dense, and the whole ball of thing grows as square root of n. That's the branching diffusion pattern. And I'm going to show you now that that's exactly what happens in string theory. Let's see. The most elementary, I don't know a lot of string theory. There are people in this audience who have put on their blogs that I am a string theorist, and I am not a string theorist. I barely know the simplest things about string theory. I know what the harmonic oscillator is. Here's an equation that every string theorist who's read Green, Schwartz, and Witten, or any other string theory book knows immediately. X of sigma and tau. This could be a closed string. I'll take an open string. An open string that has a sigma coordinate that goes along its length. It has a tau coordinate, which is light cone time. Well, the reason we're going to use light cone time is because we're going to follow this string as it falls through the horizon in a time which is very close to light cone time. Right? Way up near that light cone there. So x of t divided by the string length scale is some sum of normal modes, creation operators, annihilation operators, square roots of n, there's 2 pi's in there also, and each creation and annihilation operator goes as e to the I n tau or e to the minus I n tau. Each one of these is an oscillating thing, and this is the position relative to the center of mass. This, quite honestly, is about all I really know about string theory. Okay? Now, I can calculate from this, the sum is first of all from 0 to infinity. What I'm going to be interested in, incidentally, this direction is tau. The tau axis is broken up into smaller and smaller little pieces by omega. What is it? Omega, tau is e to the omega, or omega is e to the tau? Which way is it? One of them is logarithm of the other. Omega goes to infinity when tau goes to 0. So that means tau is equal to e to the omega, or the other way? That way, right? Tau goes like e to the omega, I think. Okay. Tau is just the light cone time, ordinary light cone time. Omega is the hyperbolic angle. The hyperbolic angle gets very light up here, but it gets chopped up into smaller pieces. So as this should be, I guess it should be minus e to the minus omega. Now we got it right. Tau is equal to e to the minus e to the omega. All right, this is what string theory tells you to think of as a particle. Now I'm interested in the mean square size of the particle, averaged over a time between the time that it passes a certain omega and the time that it falls through the horizon. I want to look at it as it falls through the horizon from a time t when it was supposed to have entered a region of a certain temperature and average it over some interval of time. It doesn't need to be this whole time. It could be half that time or whatever. That means I have to average it over some dt, over some, let's say from 0, from something to over a region delta tau. Over a little region delta tau. Delta tau now representing a small interval of omega. All right, the effect of integrating this is very modest. All it does is it cuts out the high-frequency components of A, the high-frequency A's. Each A goes like e to the I n t. If you integrate over a little bit of time, it simply puts a cutoff in here. It cuts it off and makes it from 0 to 1 over delta tau. Same thing. That's what x looks like. Now let's square it and study its expectation value to get some idea of, on the average, how big this ball of wool grows. What you're really doing is studying more and more normal modes. The reason you're studying more and more normal modes is because you get to see higher and higher frequency oscillations as you're looking from far away. Well, square this, and the answer is sum 1 over n times, that's it, times L string squared, which is logarithm of 1 over delta tau. The object grows logarithmically with cutoff, but the connection between tau and omega is also logarithmic. So what this tells you is that the size of the object is growing linearly, or the square of the size of the object is growing linearly with omega. With the hyperbolic time, so let me just say what's happening. With the hyperbolic time, you get to see the slowdown, the natural slowdown that you see from a distance allows you to see more and more and more of the high-frequency structure of the string. The more high-frequency structure of the string you see, the more fluctuation you see. Each normal mode has its own zero-point oscillations. This is just the sum of all the zero-point oscillations. They add up to something which grows logarithmically. Another way to say the whole thing is that this x is a field of dimension 0 in 2 dimensions, and its expectation value grows logarithmically with cutoff. Same statement. So what do we see? We see a thing which grows logarithmically with tau, but linearly with omega. If you also calculate the total length of string, this was done by Igor Klebanov and myself, the total length along the string, you find out that it grows exponentially with omega. There's e to the omega. So it has exactly the same properties as the branch diffusion. I'm going to show you in a little video a Monte Carlo simulation. Monte Carlo simulation just taking the wave function of the string, sampling it, and evolving it, not in time, but by adding in more and more normal modes. Adding in more and more normal modes, which is what happens when you look at the string. What you see looks like, let's see if we can turn this on.
Of course, if I will play to the statistics, then I will see nice.
Exactly.
So why should I have also kind of image?
So that's what we're trying to understand. We're trying to understand this discrepancy from what you see from the outside with what you see if you fall through.
No, but what I see from outside is Hollywood. It's nothing more. You see, I can just test the things when I fly together.
Okay. Okay.
So what's happening now? Wouldn't you supposed to grow?
Yes. Exactly. Oh yes. Oh yes. No, there's a real measurable consequence of this. When you scatter two particles together, this is what you see.
Where it's on the horizon, right? When you send them on the horizon, then bring credit. But I could describe it.
If you just scatter particles,
yeah.
All of this has implications for scattering of particles, and it tells you that the particles grow.
I mean that the energy is larger than the Planck energy.
That's right.
Scattering. Yeah,
Right.
okay. But
Right.
there
They actually grow. That's right.
there is,
That's right. This is a turnaround.
yeah.
Okay. Now, whether you think this is important or not, this is up to you. I mean, this is a matter of. Should we turn up the lights? This is just a Monte Carlo. Well, if we ever get it, let's see. Yeah, but I don't know how to get the. That's it. You see it? You see the string? Falling toward the horizon.
So black is black hole.
I don't know. Okay.
No, it's just a string with the colors.
Okay.
Yeah.
Oh.
Press the first one. There it is. It's adding modes, adding modes, adding modes. This would be in real Schwarzschild time. This is the way an open string would grow because you get to see more and more modes. This is just another sample from the Monte Carlo. They all look very similar. They all have some characteristic structures. The length scale, which means the size scale of one of these loops, a typical loop is an L string. They get denser and denser, and the whole thing grows.
So
I think
this
it's
is the image of the string which I created.
Yeah, this is-
the string is approaching.
by adding more and more normal modes into its
Yeah,
description.
but for instance, when you are calculating the thing,
Yeah,
it's just will be photograph of the string which
Yeah.
I will be created from outside, right?
yeah.
And, you
It's a
take
Monte
into
Carlo
account-
sampling of the wave function.
Right,
Yeah.
but you need to take, of course, into account that the signal which will be kind of weakly get weaker because of the exponential
Of course,
change.
of course, of course, of course. Yeah, this is a pure light cone string theory that actually has no black hole in it. It's just what happens as you take into account more and more normal modes.
Yeah, I
The
mean,
prescription from black holes tells you the number of normal modes should grow exponentially with, should grow with omega. Should grow linearly with omega. So that's what that's the very, very big difference between what quantum field theory says and what string theory would say above the string scale. The next time I'll talk a little bit about the holographic principle and about anti-de Sitter space. Oh no, I think we also have to talk about counting black holes, don't we? Oh boy. We'll talk about counting black holes and counting the entropy of black holes. I don't know how far we'll get. We'll try to finish.